The topic of this part of the course is solid-state chemistry. The purpose of this first video is to introduce some terms that we're going to need to describe the arrangements of atoms in solids. Firstly, we define a regular ordered array of atoms in the solid state as a crystal. The arrangement of atoms is called the crystal structure. The picture on the left of the screen shows a crystal of polonium. It's a pretty obscure element that you're unlikely to come across unless someone puts it in your tea, but it does have a very simple crystal structure. If we zoom in on it, we can see that structure a bit more clearly. It has what we call a primitive cubic packing of polonium atoms. Now, while the crystal consists of a huge number of atoms, like Avogadro's number, because it repeats in a regular manner in all directions, we can understand its structure by just picking out the unique repeating motif. In this case, we draw a cube, the corners of which sit in the middle of 8 polonium atoms. This cube is called the unit cell. We can reproduce the structure of the entire crystal by making identical copies of that unit cell and placing them next to the original in 3 dimensions. It's worth pointing out, however, that although the corners of the unit cell sit in the middle of atoms, so that the cell involves 8 polonium atoms, only 1/8 of each of those atoms is actually inside the unit cell. So each atom really only contains 1 polonium atom. This is obviously an important point if we want to use the unit cell to work out the density of the crystal, or if we have more than one type of atom, we'll need it to work out its stoichiometry. Now, let's just take a minute looking at the unit cell itself without worrying about atoms. Firstly, we're going to need to define its shape. We do this by starting in one corner. We're going to choose the bottom left corner, and determining the lengths of the sides, which we will label as A, B, and C. And then we also need to define the angles between those sides, and we label those alpha, which is the angle between C and B, beta, which is the angle between A and C, and gamma, the angle between A and B. Now, in the cell we've talked about so far, it's a cube, so of course in a cube, A, B, and C are all equal, and alpha, beta, and gamma are all 90 degrees. So as I already said, we can reproduce the entire crystal from this unit cell, using it to tile all of 3-dimensional space. We do this by copying and translating by integer multiples of the side length A in the x direction, like so, and then by integer multiples of B in the y direction, and integer multiples of C in the z direction. Okay, we can do this because a crystal has what we call translational symmetry. We can emphasize the concept of translational symmetry by decorating the unit cell with so-called lattice points, shown here in red. Note that these are not atoms, they're just points that are acted upon by translational symmetry. If I generate more unit cells by translation, then I get more lattice points. The significance of a lattice point is that if I do happen to put an atom on it, like so, then translational symmetry will automatically generate identical atoms on all of the other lattice points. Okay, let's go back to there. However, I'm not restricted to putting an atom only on a lattice point. I can put one whenever I want, like that, for example. If I then generate more unit cells, translational symmetry will generate more of those atoms in the same location relative to each of the lattice points. Okay, now it's worth pointing out again that the stoichiometry of the crystal depends on the contents of the unit cell. In this case, only 1/8 of each of those blue atoms sits inside the cell, so the cell itself only contains 1 blue atom in total, whereas the green atom sits entirely within the cell, so it also contains 1 green. The stoichiometry of this unit cell, and hence the stoichiometry of this crystal, of this made-up compound, is blue 1, green 1. The concept of lattice points allows us to introduce a few more complex types of cells, and these are called the 4 crystal classes. Up to now, what we've been talking about is a primitive unit cell, and that's labelled with a capital P. Primitive cells have lattice points only on the corners. However, it can also be useful to define unit cells with additional lattice points. For example, an additional lattice point in the middle of the cell. This is called a body-centered cell, and it's labeled with a capital I. Another type is the face-centered unit cell, in which we have an additional lattice point in the center of each of the three opposite sets of faces. And then finally we have the plane-centered cells. These have additional lattice points in the middle of only one of the three sets of faces. Plane-centered cells are labeled with a capital A, B, or C, corresponding to the unit cell direction that is perpendicular to the centered face. The example here is for a C-centered cell, and you can see that if you look at the three axis labels that I've put in the middle of this slide. So, unit cells we've discussed so far have all been cubic. It's pretty obvious and intuitive that we can tile all of space by packing cubes together. However, we can still tile all of space even if we distort the cube, as long as we just keep the opposite edges of the faces and faces parallel to each other, like this. There are 6 distinct ways in which we can do that, and these give rise to the 7 unique crystal systems. So the picture here shows a cubic unit cell, and it's cubic because all of the side lengths are labelled as A to show that they're equal. In this series of pictures, any angle that we don't indicate, or we don't put a label on especially, is assumed to be 90 degrees. So the simplest thing we can do to that is just stretch the cube in one direction. This is called a tetragonal cell. It has two equal side lengths and one unequal one, and all the angles stay at 90 degrees. Next we have the orthorhombic cell. This has 3 different side lengths, but it retains still all 90-degree angles. Then we go to the monoclinic cell, in which we distort one of those angles away from 90 degrees. In this example we've distorted the beta angle between A and C, but in principle it could be any one of the 3 sets. And the next step from that is then to distort all the angles away from 90 degrees. This is called a triclinic cell, and it has the lowest symmetry of all the crystal systems. There are also 2 slightly different cases. Firstly, the rhombohedral or trigonal cell, in which we keep all of the side lengths equal, but we distort all of the angles away from 90 degrees. And it turns out that if you do that, all the angles will actually be the same. So they're all labelled as alpha here. Finally, if we take the tetragonal cell and we distort the angle, 90-degree angle between the 2 equal sides to 120 degrees, a special angle, we get the hexagonal unit cell. This label is more obvious if we draw a slightly larger version, which emphasizes the hexagonal symmetry of that crystal system. If we combine these 4 crystal classes with the 7 crystal systems, we get the 14 unique Bravais lattices shown in this table. The astute among you may point out that 4 times 7 is not 14. In fact, half of the possible combinations are missing from this table. So why can't we have, for example, a C-centered tetragonal Bravais lattice? Well, the answer is that we can. I can draw one. However, if I draw a slightly larger version, then what I can do is, because this is a tetragonal cell, all of those angles on the top and bottom faces are 90 degrees. That means that if I rotate 45 degrees and connect up the lattice points, closer lattice points, those angles will also be 90 degrees. So I could draw a cell like this. Now this unit cell is also tetragonal. All those angles are 90, but it's smaller and it's primitive. So a C-centered tetragonal cell can be drawn, but it's unnecessary because it is simply a more complicated representation of a smaller and simpler primitive tetragonal unit cell. Similar arguments can be made to eliminate all of the other combinations of crystal system and crystal class that are missing from this table.